Okay, well, good morning everyone. Welcome back to our last content lecture for this term. Let's go. So in this lecture, we're going to be talking about a special data structure called tries. Right, so we'll talk about why tries are used. We'll go through all the operations on them, implement the operations as well, and then we'll also look at some applications of tries. Okay, so first of all, why do we want to explore the new data structure of tries? So really, many applications, right? There are many applications that require us to search through a set of strings using a pattern, right? So there are a lot of examples of these applications. For example, autocomplete is one of them, right? So when you're typing a word in a text message, for example, and you type a few of the letters, then your phone might suggest what words you're trying to actually type, right? So that's autocomplete. Predictive text. So predictive text is a feature of old phones where you have, your 10 buttons for each of the numbers, but for each of the buttons correspond to a certain set of letters, for example, like A, B, C, D, E, F, and so on. Right, so in order to type a word, you actually type the numbers that contain those letters, right, on those buttons. So that's predictive text. Approximate string matching is another one. So maybe there are some applications where, given a string, you want to find which other words are similar to that string, right? And by similar, I mean maybe you can get from one word to another by deleting a character, adding a character, or maybe replacing a character with something else. Right, and another example is spell checking, right? So given a series of letters, you want to check if that sequence of letters actually corresponds to a word that's in your dictionary, right? So that's spell checking. Okay, so these applications require us to search through a set of strings, right? So if we were to implement a set of strings now using the data structures that we've talked about, what options do we have, right? Let's think about the most efficient data structures that we've covered so far. So what are some examples of those? What are some efficient data structures? Yeah. Yeah, AVL trees, right? So AVL trees give us log n insert, delete, search. What is another data structure that's really efficient that we just covered recently? Yeah. Yeah, hash tables, right? Hash tables allow us to search a set of things or keys in O1 average time, right? So here are the applications, some of the applications I talked about, right? Autocomplete. So if you type GOO, right, then maybe it'll suggest good, maybe it'll suggest Google, and so on. Right. What else do we have? So predictive text is what I also mentioned before, right? So in these old phones, right, each button has a digit and a few letters on it, like A, B, C, D, E, F. So if you want to type a word, right, then you have to press the buttons that contain those letters, right? So in order to type good, for example, you would press the buttons 4, 6, 6, 3, right? Because 4 has the letter G, 6 has the letter O, and 3 has the letter D, right? But the thing is, each sequence of button presses might actually correspond to multiple words, which is interesting, right? So once you press a sequence of buttons, then you might have to select which word you actually want to type. All right, so how can we implement a set of strings efficiently? So we've already went through a few different data structures like AVL trees, right, which are log n in the worst case for all the main operations, and hash tables, which are O1 on average. Okay, so maybe we could use these in order to implement these applications such as autocomplete and predictive text, right? But it turns out that we can't actually do that really efficiently. That's because even though these data structures are efficient, right, they're not really efficient when we're just searching for a pattern, right? So, for example, with auto-completion, right, if I want to find, suggestions after I type a few letters like GOO, how do I actually do that if I have a hash table, right? You can't really do that because when you search in a hash table, you need to pass the entire key into the hash function, right? And then the hash function will tell you where to find the word or whatever, right? So hash table doesn't really work if you only have part of the key that you're searching for, right? Such as the first 3 letters. So hash table isn't going to work quite well. The only really way to search a hash table if you have only the beginning of the key is to actually just search through the entire hash table and look at every key to see if it starts with those letters, right? So hash tables don't work really well. Even tries, so if you want to search a try for words that start with a few letters, that's not going to be very efficient. Right, and if you go to the next application like predictive text, then if you get a series of button presses like 4663, then how can you search a hash table for all the possible words that match that sequence of button presses, right? You can't really do that because each button corresponds to multiple letters, right? So, if you wanted to search for all the possible keys, you'd have to search all the possible combinations. For example, if you pressed 4663, then you have to search GMMD, GMME, and so on, right? So it's hard for these data structures when you want to search for patterns, right? And one possible solution that can help us solve pattern matching efficiently is tries. Okay, so what is a trie? So trie is a tree data structure, so a tree-based data structure, and it's used to represent a set of strings. Right, so for example, maybe we can use it to store all the words in a document, all the words in a dictionary, so that when you do your autocomplete, you can find all those possible words. And we're going to call these keys or words, all right, interchangeably. Okay, and the nice thing about the trie is that it supports string matching queries in O of m time, right, where m is the length of the string being searched for. Right now, that is way faster than O of n, right? Because O of n is usually the number of keys in your data structure, right? So you probably have lots and lots of words in your hash table or your AVL tree or your trie, but m here actually just represents the length of the string, so the number of characters in your string, right? Which is usually going to be a lot less than the number of words that you've stored. All right, so much more efficient. And just a fun fact about the origin of the word try, so it comes from retrieval, right? But it's pronounced as try, not tree. Okay, so here is an example of a try. Okay, so one thing to note here is that we have a root node, right, because it's a tree, and then each node has a set of children that correspond to particular letters, right? For example, the root node has child nodes corresponding to A and E. The A here contains nodes corresponding to C and P, and note that the same letter can appear in multiple places in the trie, right? And another thing is that this isn't necessarily a binary tree, right? A node can have more than 2 children if needed. But even though in this tree, each node has only 1 or 2 children, there could be a lot more children. All right, and another thing to notice is that some of these nodes are highlighted in red, right? They're outlined in red, and we'll explain what that means later. But at the moment, here are the different keys that are stored in the trie, right? So we have ace, aces, ape, apes, app, apply, early, earth, and east. Right, so if you look at this for long enough, you'll probably notice that each key is pretty much just a path in the trie, starting from the root. Right, path down the trie, starting from the root, that ends in one of these red nodes. Okay? Okay, so a little bit more about tries. So each link in the trie, so each of these edges, or you could think of them as pointers, represents an individual character. Okay, so each link here, so even though I've written the letters in the nodes themselves, it is really the link here that corresponds to the character. So this link, for example, corresponds to A, this link here corresponds to C, this link corresponds to P, and so on. Okay, and a key is represented by a path in the trie, as I explained earlier, right? And also each node can be tagged or marked as a finishing node, right? So these red nodes are finishing nodes, and a finishing node marks the end of a key, right? For example, since this node here is a finishing node, this marks the end of a path or a key in the trie, ACE, ACE, right? And another example is that even though we do have a path in the trie here, which is EAR, right? Because the last node on this path here is not marked as a finishing node, that means the word ear is not in the trie, okay? So important thing to remember. Okay, now each node can also contain some data associated with the key. Right? For example, if you're using a trie to implement a dictionary, for example, then each node might contain some extra information about the word, for example, the definition. Right? And finally, another important thing is that unlike a search tree, like a binary search tree, AVL tree, the nodes in the trie don't actually contain the full key, right? So, for example, this node over here, right, doesn't actually contain the full word ACE, right? ACE. So the words aren't stored in the nodes themselves, but the keys are implicitly defined by their position in the trie, which I've written here. Right, so this node here corresponds to the word ACE because it's the last node on the path ACE, right, and so on. Okay, so here is how we represent a trie. This is one way of representing a trie. I mean, it's the basic way of representing it. So first of all, we have a notion of how many unique letters there are in our alphabet, right? So since we're considering English here, the alphabet size is 26, right? And each node contains an array of pointers, right, of the same size as the alphabet, right? So this node here contains 26 pointers, an array of 26 pointers to potential child nodes, right? Now, it's possible that some of these children might not exist, so the pointers would be null, but you might be thinking right now that this is a lot of space, right, for a node. So, isn't that gonna, use up a lot of memory on your computer? Yes, it would. And we'll discuss ways of, saving space a bit later. Okay, and what are the other fields? So we have a Boolean called finish, which marks the end of a key, right? So if this field is true, that means that node is a finishing node. And also we have potentially some data, right? So each node might contain some extra data associated with the key. Okay, so here is an example. So this trie is, so this diagram doesn't actually show us how the concrete representation of the trie works. This is kind of an abstract view of the trie, but this is how it would be represented in memory, right? Every node contains an array of 26 pointers, and each node also contains a Boolean that indicates whether the node is a finishing node. So F here, if there's an F, that means it's a finishing node. right? And remember that the nodes themselves don't contain any characters, right? They don't, for example, this node here doesn't actually contain the letter S in it. The letters are implicitly defined by what index the pointer is stored at, right? So for example, this pointer here is at index 4 in the array, right? So that means it corresponds to the letter E, right? Because 0 corresponds to the letter A, 1 corresponds to the letter B, and so on. Okay, so yeah, question?
Why don't we do that instead of just storing the actual alphabet in the key itself?
Sorry?
Why don't we store the alphabet in the node itself?
So we could do that, but it would be redundant in this representation. So that's because each index corresponds to a specific letter. So since this, for example, this index here, there's a pointer at index, I'm not sure what it is.
The integer corresponds to S, yeah, but like why don't we just put the letter of the node itself?
So we don't need to do that because the information can already be deduced from what index.
We need to have an array of each struct node.
Yeah, so we have an array where each index corresponds to a specific letter. Yeah. So this S, for example, is stored at index 18, I think. So since there is a pointer at index 18, that means it corresponds to the letter S. Yeah. Okay, so that's the concrete representation, right? So keep this in mind whenever we show a diagram of a trie, this is what it actually looks like in memory. And now we can start talking about the different operations on our tries. So how do we actually insert into a trie? Well, first of all, when we create a trie, it only contains the root node, right? So when we create a new trie, that will just create a new root node and return it. So how do we start inserting things into the trie? So the process is first we start at the root, just like with any kind of tree, binary search tree, where we start at the root. And for each character in the key from left to right, we're going to check if there is a node corresponding, if there's a child node corresponding to that character, right? And if there isn't a node corresponding to that character, then we're going to create one, right? And then we're going to descend into the child node. Right, so we're going to keep doing this for each character in the key. So we're going to basically walk down the tree, each time creating a new node if there isn't one. And at the end of that path, we're going to mark the resulting node, so the final node, as a finishing node. And then if there is any data to insert, then we're going to insert that data. Okay, so let's look at an example. So we want to insert these words into a trie. Okay, so at the beginning, the trie just contains a root node, right? So when we insert the word C, right, we want to create a path in the trie corresponding to SEA, right? So since at the beginning the trie doesn't actually have any nodes, that means we're going to have to create 3 new nodes, right? The root node is going to point to S, the S is going to point to E, the E is going to point to A, right? So like that. And the final node is going to be marked as a finishing node. Okay, the next word is shell, right? So if we want to insert shell, then we iterate through the characters from left to right. So first of all, we have S. Right now, the root node has a child node corresponding to S, so that means we just go down to that node, no need to create any new nodes. But then this S doesn't have a child node corresponding to H, right? So that means we're going to have to create a new path starting from this S with the letters H, E, L, L, okay? Like that. Okay, next word is cell. Okay, so if we go through these letters from left to right, there is a path with the letters S and E, right? But after that, there is no L. So that means we're going to have to create two new nodes starting from this E, which correspond to LL, right? Like that. Next, if we want to insert the word shore, right, then we're going to see that there is already two nodes corresponding to S and H, right? But there is no O after that, so we need to create three new nodes containing O, R, and E. Okay. And finally, if we want to insert the word she, right, then going through the letters from left to right, we see that there is a path corresponding to the letters S, H, and E. Right, so that means we don't need to create any new nodes this time, but we just need to set this last node to a finishing node. Okay, and that's it. That's the changes to the trie. Okay, so there is our final result. And here is the pseudocode for inserting into a trie. Right, and this one is recursive, but you can implement this iteratively as well. That's because we're only going down one path in the trie, right? So whenever you only need to go down one path, you can implement that iteratively. Okay, so let's walk through this pseudocode and see what's going on. So the input is a trie, a key, and some associated data. Okay, and what happens, so first of all, if the trie is empty, right, then that means we've descended down a path, and at some point, we no longer have a child node, right, to continue our path. So what we need to do is create a new node, right? So T equals new node. And notice that we're not returning T right away, right? That's because we might need to create multiple nodes when we're inserting a key. So we just create our new node, and then we just check a few things. Right, first of all, if M is equal to 0, so if the key is empty, that means we've reached the end of our path, right, in our walk through the trie. So that means T is going to be the last node on this path. So we're going to set the finish boolean to true. So we'll mark it as a finishing node, and we're going to insert the data. Okay? So that is what happens if we reach the end of our key. Otherwise, we're going to grab the first character from the key. Okay? And then we're going to also extract everything from the key except for the first character, right? So this is some special notation here in our pseudocode, which just means remove the first character from the key. Right, so rest equals key from index 1 to n-1. And what we'll do is we're going to recursively insert into the trie at this index corresponding to the first character in the key. Right? And then we're going to pass in the rest of the key, so everything except for the first character, and also the data. Right? And at the end, we return our new subtrie. Okay, so let's go through and try and implement this. Data is any information associated with the key. For example, if you have words and definitions, then definitions would be your data. Yep. Okay, so let's try and implement this. Okay, so in my trie.c, I've already implemented trie new, which creates a new trie. So what it does is it just allocates trie, so a trie node. And let me first show you what a trie node actually contains. So here it just contains an array of children, right, of size 26, and also a finishing boolean. Okay. So no data, because data is not really relevant here, but let's look at the rest of this code. So trie new just allocates one trie node and returns it. trie free, recursively freeze all the nodes in the trie, and insert. Okay, so here is insert. Now, what is going on here? Okay, so all right, so here, let me actually remove everything. So, okay, so yeah, let's try and implement trie insert. Right, and we'll just follow the pseudocode, right? So what does our pseudocode say? So if our trie is empty, right, then we're just going to create a new node. Okay, so if t is null, right, then we're going to set t to be a new node. So what I'm going to do, I'm going to calloc a new node. So calloc one size of star t. Okay, and that's it. And of course, you might want to do some error checking. So here I'll just say assert t not equal to null as a quick form of error checking. Okay, and what do we do now? So first of all, if m equals 0, so this means if the key is empty, right? So here I don't actually have an m variable, but the key is empty if this string is empty, right? So how do I check if a string is empty? That means the first character should be a null character, right? So if key at index 0 is the null terminator, then I'm going to set t to be a finishing node, right? So t finish equals true, and I don't need to set any data here because we don't have any data. And otherwise, I'm going to figure out what the first character of the key is. So first equals key 0. Right. Now I need to figure out a way to remove the first character from the string. Right. Now in C, you can actually do this by just creating a pointer to the second character in the string, right? And that actually corresponds to the string, except with the first character removed. Okay, so let me show you how we can do that. So char star rest equals the address of the second character, right? So the address of key 1, right? Now that's going to point to the whole string except with the first character removed. Okay, what's going to be next? So t children. So what we're going to do is we're going to recursively insert into the index corresponding to the first character of the key. Right, so t children first. Right, so that's the first character in our key, equals try insert t children first, and then we pass in the rest of the key, which is rest. Okay, and this is kind of similar to inserting into a binary search tree, right? Remember, you in BST insertion, you would see code like t left equals BST insert t left, and then you pass in the value. Now this is similar, except because we're dealing with an array of pointers, we're selecting which pointer we want to insert into, right, by using this indexing. Okay, and at the end of the function, we return t. Okay, so that's how we implement try insert. Okay, so now, oops, here we're going to just compile. Right, and we'll just go through this example of inserting these words. So test try. Right, so in my test program, right, I insert all of these words. Let me actually remove, so let me actually ignore this part of the program first. So we just want to test insertion. Okay, so now if I insert these same words, as in our example, see, shall, sell, shore, she, then we're going to get this nice trie, right? So notice that the root node has one child, which is S, right? This S here has two children, E and H. Right? This E has two children, A and L. This A is a finishing node, right? Because it's the end of the word C. This L here is a finishing node because it's the end of the word sell, S-E-L-L. And then we have some other keys in the trie like she, shall, and shore. Okay. Okay. So there we go. That's insertion. Okay, now how do we implement search? Right, now search is really similar to insertion. Right, just like a binary search tree. You know, when we search in a binary search tree, you pretty much, you know, just go through and try to, well, insertion is similar to search in a binary search tree, right? Where you go through the tree and once you hit null, you insert the node there. But in a trie, when we want to search for a key, then once again we start at the root node, right? And for each character in the key from left to right, if there is no child node corresponding to the character, then that means the key doesn't exist in the trie, right? So we're going to return false. Otherwise, we just move down into the node corresponding to C. Okay, and if the node that we end up at, so the final node on this path is a finishing node, then we return true. Otherwise, we return false. Okay, so let's look at some examples. All right, so here I have this trie, and first I'm going to search for the word early. Okay, so in order to search for this word, starting at the roots, right, we're going to go through each character one by one and try to descend into the child node corresponding to that letter. Right, so first we descend into E, right, then we descend into A, then we descend into R, then L, then Y. Right, and the final node on this path is a finishing node, so that means early is in the trie. Right, so 1, 2, 3, 4, 5. Okay, so we found the key. Let's look at another example. So we want to search for the word apple. Okay, so if we try and follow a path down this trie with these letters, then A, we'll get to A, then P, then L, but L doesn't have a child node corresponding to E, right? So that means apple is not in the trie. Okay. So the node for apple has no child node for E. Okay, and next, let's search for the word ear. Right now, if we follow a path down the trie corresponding to these letters, then we will find the node there will be a node at the end of this path, right? EAR, but this node is not a finishing node, right? It's not marked as red here, which means the key ear isn't actually in the trie, so it's not a finishing node. Okay, so so these are some examples of search. Now here's the pseudocode for searching in the trie. Right, so a little similar to insertion. Right, now so our input is a trie or subtrie and a key of length m. So if the trie is empty, then we're going to return false, right? Because that means the word that we're searching for isn't in the trie. We've gone down a path in the trie, but eventually we've hit null, right? So we can't go any further. Otherwise, if m equals to 0, so if the key is empty, then that means we've gone through we've gone through every letter in the trie, and we've descended and found the last node on the path. Right, so after that, all that we need to determine is whether that node is a finishing node or not. Right, so we return a comparison between the finishing Boolean in our node and true. Right, so if tFinish is equal to true, then that means that word exists in the trie, otherwise it doesn't. And otherwise, that means we haven't reached the end of the key yet in our trie. So what we're going to do is, again, grab the first character of our key, grab the rest of our key, right, and then recursively search the child node corresponding to the first character in our key. Okay, so let's try and implement this. Okay, so the function that we want to implement is try search. Alright, so this function returns a Boolean, and it takes in a key. Okay, and what does the function do first? Well, it checks if t is empty, right? So if t is null, then we're going to return false right away. Okay, otherwise, if the key is empty, so key at index 0 is equal to the null terminator, then we return tFinish, right? So once we reach the final node on that path, the finish Boolean is going to tell us whether the key is in the trie or not. Right, finally, we're going to extract the first character from our key, so key 0. Then we're going to grab the rest of the key, so everything except for the first character, which is the address of the second character, so ampersand key 1. And then we're going to just recurse into the child node corresponding to the first character. Right, so return try search t children first, and then we pass in the rest of the key, rest. Okay, so that's how we implement try search. And now if we just compare it to what I have here, it's the same, right? Except I just have else if and else here. All right, so let's get rid of this. Okay, so that's try search. Right, and now let's modify our test program a bit. So first of all, let's try some cases similar to the ones that we've discussed here. Right, so if I have this try, which is the same as the one that I've created in the test program, then let's search for the word shell, for example. So we're going to assert that the word shell is in the try. Right, what other cases do we have? So we had a case where there isn't a path corresponding to the characters in the word. So let's try try searching for the word seal, so S-C-A-L, right? Now that word shouldn't exist, so we'll put an exclamation mark in front of try search. Right, so seal isn't in the try. What else? So let's try the word shout. So shout is not in the try. And let's try, so what I'll do is I'll remove the word she, so I won't insert this word, and then I'll check using assert that the word is not in the try, so she. Okay. So we've got these asserts, and now if we run our test program and, okay, so let's see, what is this? So array subscript is of type char. Okay, so don't need to worry about that, but I'll just change this to int instead. Okay. All right, so when I run the program, we get an error, which is not what I expected. So line 56. Okay, so let's see, what do we have here? Line 56. So T first, rest. Okay, so what does the error say? It's a heap buffer overflow. It's a read of size 8. Located 40 bytes before 216 byte region. Fine. So, and the stack trace tells us that was allocated. So we're 4 letters in. Okay, let me actually make sure that the program works fine without these, without any calls to try search. Okay, so it does work. So maybe let's see what's wrong with our program. First. Didn't do minus a, you're right. So yes, actually, yeah, this is what happened here. So I need to do minus a, you're right. So a is, the character a represents, is actually a number, right? It's the ASCII code corresponding to a, and I need to subtract a. Yeah. Okay, cool. So now this should work. So if I go back and uncomment this stuff, right, so it should now pass all the tests. Thanks for that. So yeah, so remember to subtract a, I guess, next time. All right, so that's insertion. Sorry, that was search. And now let's look at deletion. Okay, so deletion is trickier than insertion and search, right? And that's because when we delete a word or key from the trie, we might end up with branches that don't contain any data. So this is what I call dead branches here. So what we could do is just find the node corresponding to the key and then unmark it, right? So we just don't mark it as a finishing node anymore. But this can leave behind dead branches, right? Which wastes memory. So here's an example of that. So if we have this trie and then we delete the word shore, right? S-O-H-S-H-O-R-E, then if we just set this node to be a non-finishing node, right, then we end up with a branch that doesn't actually contain any keys, right, which is a waste of memory. Okay, so how do we avoid this problem of having dead branches? So here's what we can do. So first we find the node corresponding to the given key, right? Then we're going to mark the node as a non-finishing node, like I described earlier. But then we want to clean up the trie, right? If it ends up with a dead branch. So what we do is, starting from that final node in the path, right? If that node is not a finishing node and it also has no child node, so it's a leaf node, then we're going to delete that node and move up to the parent and repeat, right? And this moving back up the trie and deleting the node if it is a non-finishing node and it doesn't have any children is handled recursively, right? Similar to balance checking in an AVL tree, right? The balance checking happens on the way back up the trie, the AVL tree. Okay, so here's an example. So if we want to delete the word ace, right, then we're going to go down the trie, find the node corresponding to ace, and then we're going to mark this as a non-finishing node. Right? And then we don't need to delete any nodes here because this node E actually has another child. So we just unmark it. Here's another example. Apply. So if we want to delete this node, delete this key, then we're going to go down to the node corresponding to apply and unmark this. Right? But the problem now is that there are two nodes L and Y which are both non-finishing nodes and they don't have any data. Right, so what we're going to do is, since after we unmark this node, the node doesn't have any children, we're going to delete this node. Then we're going to move up to the L, right? And since this node is also not a finishing node and it is a leaf now, we're going to delete this node as well. Then we'll go up to P, and since P is a finishing node, we stop deleting things. Okay, and that's all we get. Another example is deleting Earth from this trie. So if we delete Earth, then we'll go down to this node over here, unmark the H, and then we're going to delete the H since it has no children. And then when we go back to the T, we're going to delete that as well since it is a non-finishing node and it has no children. And once we go up to the R, we're going to stop, right? Because R has a child. So that's what we get. Okay, and here is our pseudocode for deletion. Okay, so if our trie is empty, that means the word doesn't exist, the key doesn't actually exist in the trie, then we just return. Otherwise, if m is equal to 0, then we're going to mark the node as a non-finishing node. Right, so we've reached the ends of the key, and we're going to mark the node as a non-finishing node. And otherwise, if we haven't reached the end of our key, then we're going to recursively delete from the subtrie corresponding to the first character. Right? So using the same technique as before. Okay, and now after we've recursed and deleted the key from our subtrie, we need to do a final check. Right, this is to clean up any dead branches. Right, so if the current node is a non-finishing node, right, and it has no child node, so it's a leaf, then we free the current node and we return null. Right, so we are cleaning up this node because it's just a waste of memory. And otherwise, so if the node is a finishing node or it has some child nodes, then we return the node instead. Okay, so let's implement trie deletion, and this time we'll remember to subtract a from the character. Okay, so our function is going to take in a trie and a key. Right. And first of all, if the trie is empty, then that means the key doesn't exist, so we're just going to return back an empty trie. All right, next, if we've reached the end of our key, so key 0 equals the null terminator, then we're going to unmark the node. So the node is no longer a finishing node. Right, and what else do we need to do? That's it. Okay, otherwise, we're going to grab the first character from our key. So first is going to be key 0 minus a this time. So remember to adjust so that 0 corresponds to a, 1 corresponds to b, and so on. Then we're going to grab the rest of our key by doing this ampersand key 1. Then we're going to recursively delete from the subtrie corresponding to the first letter. So t children first equals trie delete t children first rest. Okay. Right, and finally, we need to do some cleanup. Right, so what was this if statement? So if the node is not a finishing node and it has no child nodes, right now this second part of the if statement is not so easy to check, right? You have to create a for loop to go through the entire array of children and check that each of them are null. Right, so let's just create a simple helper function for that. So we'll say bool is leaf node, and in this function we are just going to go through, iterate through all the pointers in the node. Right, and if t children I is not null, so if it's not null, then that means it's not a leaf node, so return false. Otherwise, if we go through the entire array and all the pointers are null, then that means it's a leaf node, so we return true. Okay, and then we can now write our if statement. So if t is not a finishing node, not t finish, and t is a leaf node, then we are going to return null, but not before freeing t. And otherwise, we're just going to return t. Make this a static helper function and put the function prototype at the top. Okay, so there is our delete function. Now, hopefully this doesn't bug out like before. So let's go back to our test program and uncomment some of this stuff. Okay, so now, so what we have is this trie over here, right? And we're going to test out deleting the word she, right? So let me re-add the word she into the trie, and then I'll delete the word she, right? And what we'll see is that none of the nodes should actually be deleted, right? And let me comment out these search tests. Right. The only difference is that the node corresponding to she should no longer be marked as a finishing node. So now if I compile the program, oh yeah, I actually rewrote the function. So let's go and delete that function. Okay. So test try. Okay, so here is our original trie, right? So notice it contains the word see, cell, she, shell, and shore. After we delete the word she, E is no longer marked as a finishing node. right? And that's the only change that happens. Now, what are some other cases? So let's delete the word shell from this word, from this trie. So if we delete the word shell, then these two nodes should be gone, right? So let's go back into our test program and delete shell instead of she. Compile and run. Right, and notice that we no longer have these two nodes, L and L, right, after S, H, and E. All right, so that works. And finally, let's test the case where we delete sure, right? And what should happen is that these three nodes, O, R, and E, should all be deleted. Okay, and the H wouldn't be deleted because it has another child node. All right, so delete the word sure. All right, and now when we run our tests, right, notice that the word sure, or the three nodes O, R, and E, have been deleted. Okay, so that's how we delete from a trie. Okay, so that is deletion. Right, and what is the time complexity of all of these operations, insertion, search, and deletion? Well, these are O of M, right, where M is the length of the given key. Right, that's because whenever we insert, search, or delete for a key, we're just traversing down M nodes in the trie, right, where M is the length of the key. Right, and what is the space complexity? Space complexity here is relevance, right, because each node actually does consume quite a lot of space. Well, it's O of n times R, right, and n here corresponds to the total number of characters in all of our keys, and R is the size of the alphabets, right? Now, R here is a variable because different languages might have different alphabets, so and the size of the alphabet can actually get quite large, right? So we need to take this into account in our time complexity. So O of n times R space. Okay, so yeah, so that's the analysis of a trie. And as I mentioned earlier, a trie that's implemented in this way, where we have an array of 26 pointers or more, depending on the language, does consume a lot of space, right? So right now we'll take a 5-minute break, but afterwards we'll talk about how we can different variants of tries that can help us save space. Okay. Cool, so let's continue on. Okay, so why aren't we satisfied with our current implementation of tries? Right, that's because it uses up a lot of space. Right, each node contains 26 pointers. Right, each pointer is 8 bytes. Right, in a 64-bit system, so 26 times 8. Right, that's more than 200 bytes for one node. Right, which is too much. So what I've written here is that our simple, naive trie representation uses an enormous amount of memory. Right, so if our trie contains, and the thing is, right, most of the pointers in the nodes are going to be unused, right? So it's going to be a lot of wasted space. Okay, so let's see. So in order to try and save space, we have different variants of tries, right? So different representations, right? But the downside, of course, to using these representations is that they're going to take more time, right? So searching them, inserting, deleting is going to take a bit longer. And I think this is a nice example of the trade-off between time and space that you usually get in computer science, right? The more efficient you want something to be, usually the more space it's going to take, the more memory, right? So here are some different ways we can change our trie representation. First of all, we can use a linked list to store the child nodes instead of an array. Another thing we can do is to break each character into smaller chunks, right? And what that's going to do is reduce the number of pointers that we need in each node. All right, so we'll see what that means later on. But first of all, let's look at our linked list of children representation. So what we'll do is, instead of an array of alphabet-sized pointers, each node is going to store a linked list of children. Okay, so here's what that would look like. So in our node struct, we would have, instead of an array of children, we're going to have a pointer to the first node of a linked list, right, where each of these nodes contains a character, a pointer to the next node, and a pointer to the trie node. Okay, so instead of this, where we have an array where we have pointers at the indices corresponding to E and H, we have a node that contains a pointer to a linked list, right, containing E and H, where each of these contains a pointer to a trie node. Okay, so because we no longer have an array of 26 pointers, we now need to actually store the character in the node itself, right? Because now there's no way to actually determine what letter the node corresponds to unless we store it, right? So we can no longer implicitly determine it from the index that the pointer is stored at. Okay, so consider this trie over here. Right, so this trie contains the words A and 8 at, B, bid, bow, and do. Right, here is how I would represent it. Well, here's the concrete representation, right, which looks a little scary, but what it is the root node contains a linked list containing the letters A, B, and D. Right, each of these has a pointer to a trie node, right, to its trie node, and so on. Right, so this node over here contains a linked list containing N and T, each of which have a pointer to a trie node. Okay, so that's the concrete representation. But it turns out that since each of these linked list nodes is always going to have a pointer to a trie node, what we can do is merge these together, right? So we can take this linked list node over here, merge it with this trie node, take this linked list node here containing B, merge it with this trie node, and so on. And what we get is a trie node that contains a character, a pointer to the first child, right? A pointer to the next node in the list of children called sibling, a Boolean, which indicates whether the node is a finishing node, and some data, right? And this is a kind of binary tree, right? Because each node has 2 pointers, right? The first pointer points to the first child, and the second pointer points to the sibling, right? And this is called the left child, right sibling representation. Okay, so if this is our trie, this is our abstract view of the trie, this is how we would actually represent it in memory, right? So each node, for example, A has a pointer to its first child, right, and a pointer to its sibling, its next sibling. So, for example, if we wanted to check if the word, bow is in the trie, right, then first, starting from the root node, we would want to check if the root node has a child corresponding to B. So that means we go to our children pointer, which points to our first child. Then we go through our sibling pointers to find a node that contains B, right? And once we've done that, so this is the node that we end up at. Then we see if this node has a child corresponding to the letter O, right? So that means we go to the first child, then we iterate through the sibling pointers and find a node containing O. Then we repeat for W, and we found the word bow. Okay, so this representation uses a lot less memory than the array representation, right? Because each node only contains, 2 pointers, right? And then 1 extra character. So that's a lot more memory saved, but finding a key is actually going to take more time now, right? Because you can't just index directly into the array to get to the child node. You have to loop through a linked list of children. Okay. So as I said before, this representation uses much less space, right? But searching, inserting, deleting is going to take more time. Right? That's because you need to, every time you want to look for a child node, you have to start from the beginning of that linked list. So you have to traverse potentially up to the same number of nodes as the size of the alphabet, right, before reaching your desired child. Okay. So that is, both the upside and the downside of this representation. Okay, so here's another variant of trie, or another way to reduce memory usage, which is called alphabet reduction. Okay, so what we do here is we take our characters, assuming that the characters are 8 bits, we're going to take them and break them into 2 4 bits, or it's called nibbles. Right? And nibbles is actually a real term, you can look it up. And what this ends up doing is that since you break the character into 2 4-bit characters, I guess, if you have an 8-bit character, then there are 256 possible values, right? But if you have 4-bit characters, then each character has 16 possible values. So you dramatically reduce the branching factor of your trie. Okay, so here is an example. So the word C contains these bytes, right? So S is 01110011, E is 01100101, and A is 01100001. So what we can do is break it into 4-bit nibbles. So S is now broken down into 0111 and 0011. E is 0110, 0101, and so on. So now instead of storing the word C, we're going to insert this word, right, which consists of 6 different characters. Okay? So yeah, that's alphabet reduction. And now this allows us to store fewer pointers in each node. Okay, so this representation uses less space because, as I said, fewer pointers per node. But again, it's going to take more time to search, insert, or delete something, right? Because the path to each key or word is twice as long, right? That's because we've broken up each character into 2 smaller characters. Okay. Finally, we have the idea of compressed tries, right? So in a compressed trie, each node can contain more than 1 character, right? And the way we get a compressed trie is we take our original trie, which has only 1 node, 1 character per node, and we merge non-branching chains of nodes. Okay, and the details of how it works is if a node is a non-finishing node and it has only 1 child, then it just gets merged with its child. Okay, and here is an example of compressed tries. Okay, so here is the original trie, where each node only has 1 character. And in order to merge this, and by the way, in this diagram, the squares represent finishing nodes. Okay, and this is what it looks like when we compress it. Okay, so for example, these 2 nodes here, A and R, right? A is not a finishing node, and it has only 1 child node, so we merge it with its child. So at the compressed trie, we have 1 node containing A, R. Okay, and another example is the word cell here, right? This node E is not a finishing node, and it has only 1 child node, so it gets merged. And this L is a non-finishing node, and it has only 1 child node, so it's merged with L, this L. So we get 1 single node containing the letters E, L, L. Yeah?
In the merged version, how do we know which character is the finishing one?
So how do we know which character is the finishing one? So it's always going to be the last character. So if your node has multiple characters, the last character is your finishing character. Yep. Yep, so this trie here contains bear, bell, bid, bool, buy, sell, stock. So this is an interesting case because it's a non-finishing node that has more than 1 character. But the word stock is in the trie, and also the word stop. Yeah. Okay, but as you can imagine, this is much harder to implement, and also a compressed trie is going to be harder to modify, right? So usually you compress a trie and then you don't modify it again. Okay, so these are the different variants of tries. Okay, and now does anyone have any questions, first of all, about the different variants? Okay, so if not, we'll have a look at the applications of tries, some applications. So one possible application is word finding, right? So suppose you have a large document and you want to be able to search the document efficiently, right? So you want to be able to type a word in, and then you get to see, where that word appears throughout the document. Okay, so what you can do is, first of all, before you start searching the document, you can pre-process it, right? So you go through the entire document, process all the words, and store them into a trie, right? And you can also store the location of where the word occurs as the data in your trie, right? Remember that in a trie, you can store some data associated with the key. So here we can store the location as the data. Right, and now when the user searches for a word, so after we've done the pre-processing and we have our giant trie of all the words, when a user searches for a word, instead of going through the entire document to find where the word occurs, you can do a lookup in the trie for that word, and then the trie will tell you where the word occurs. Right? So, for example, suppose here is our document. It's fairly small, but just for example's sake. Right, so here is our document, and each character in the document is indexed. Right. And in our trie, it tells us where each word occurs. Right. So, for example, with the word cell, right. So this last node here contains the number 12, right, and that tells us the word cell occurs at index 12 in the document. Right. What's a word that occurs lots of times? Stock. Right. So the last node on this path contains the numbers 17, 40, 51, and 62. Right, and that tells us that the word stock appears at the indices 17, 40, 51, and 62. Right, so if you have a really, really large document, then this trie will allow you to easily find where different words appear. Okay, what are some other applications? So we've already talked about autocomplete, right? So what autocomplete is given a series of letters, find all the words that start with that series of letters. Right, so let's think about how we might implement this if we're given a trie. Right, so if we already have a trie with the entire dictionary of words, how do we implement autocomplete? So does anyone have any ideas? So you're given a trie, you're given a series of letters. How do you find all the words starting with that series of letters? Any ideas?
I assume every word would have some sort of likelihood value assigned to it, and then you go the word so far, you traverse down to it and then pick the top results.
So we've actually included the idea of likelihood here, because some words are more likely to be suggested than others, or likely to be typed than others. But assuming that we're just trying to find all the words that start with a series of letters, we'll just descend down the trie using those letters, right? For example, G, O, O, and then basically all of the words in that subtrie are potential suggestions, right? So let's try and implement this. So autocomplete. Here I have a set of words. Okay, and I'm trying to autocomplete the letters G, O. Okay, so let's try and implement this. So first of all, I need to descend down the trie using the letters in my prefix, right? In my string. So I'm going to use this function to do that. Okay, so first of all, let's deal with our base case, where if our trie is empty, then there are no words to suggest, right? So we just return. Okay. Otherwise, if our prefix is empty, right, then that means we've reached the node, right? corresponding to the prefix. So now I'm going to start printing out all the possible words. Right, so let's just add a comment here. Print out all words in this subtrie. Okay, and then we'll implement that part later. But otherwise, if we haven't reached the end of our prefix yet, right, then we're going to just recurse and pass in everything in the prefix except for the first character. Right, so let's call autocomplete on, well, first of all, I need to grab the first character. So first character equals prefix 0, and I need to subtract by a to adjust the index. Right, then we'll get the rest of the key, of the prefix, I mean. And then we'll recurse on the subtrie corresponding to the first character. So T children first and rest. Okay, so now I need to print out all the words in the subtrie, right, if we reach the end of the prefix. The problem is that in our simple trie representation, the nodes themselves don't contain keys, right? In a trie, the nodes themselves don't contain keys. So as I traverse through my trie, I'm going to have to build up my string, right, as I go along. Right, so I can't rely on the nodes containing the keys, and I can just print it, so we can't do that. So what we have to do is create a string and then store letters into the string as we traverse down the trie. Okay, so let's create a array of characters for that, and we'll just assume here that no key is going to be longer than 99 characters. All right, just for now. All right, then we're going to copy the prefix into the key. All right, so because that's the part that we've already kind of traversed. So we'll use stir copy to copy the prefix into the key. Right, and now I'm going to call my helper function. Let's call it do autocomplete. Right, we're going to pass in T, which is our trie or subtrie. We're also going to pass in the array key, and we're also going to pass in what index of the key I'm up to. So how many characters have I already seen, right? So that we know where to insert the next character as we go down the trie. So let's call stir len and pass in the length of the key. All right, now I'm going to implement my helper function. So try, pass in our key, right? Or we can write it like that, but it's the same thing. And we pass in which index I'm up to in the current, in our key. Okay, now in this function, what we're going to do is to traverse the entire subtrie, right? But while we're doing that, if our current node is a finishing node, then we want to print out the key, right? So first of all, let's deal with our base case. If t is null, then we return. Right, now we want to check if the current node is a finishing node, right? Oops. So if our current node is a finishing node, then I want to print out the key. Okay, so let's try printing the key, and there may be problems with this that we can fix later. And we don't want to just return after printing the key because, you know, there could be other words underneath that need to get printed as well. So we're going to recursively traverse all the subtries of the current node. So, okay, so we're going to loop through all our child pointers, and if t children I is not null, then we're going to store the character corresponding to that child into the key array. All right, so that means key I equals a plus I. Right, so if I is 0, then that means we're going to be storing A. If I is 1, that means we're going to be storing B, and so on. Okay, and then we're going to recurse into the child node. So do autocomplete t children I key, and we're going to add 1 to I. Right, that's because the next character is going to be inserted 1 spot after the place where we stored the current character. All right, so okay, so let's now run this. Hopefully it compiles. Okay, so I forgot the type. All right, let's add that in. Static void. Right, and static void. Okay, so now let's go back to our test program. Whoops, it's just autocomplete.c. So what words are we expecting? Right, so we're expecting, if we start with go, we're expecting goop, good, gold, and that's it. Okay, so let's run the program, complete, and we end up with 4 lines, right? Which corresponds to, we also want to print out the word goody. So we print out 4 blank lines, which means that we are printing out the right number of things, but we're just printing out empty string, right? So let's try and see what's wrong with our function. Okay, so yeah, anyone have any ideas? Is the null terminator missing? So I think you might be right. So we want to add a null terminator to the key before printing it. So let's go key I equals null terminator. Then we can print out the key. Okay. Oh, yeah. So I actually noticed what was wrong. So we are reusing the same variable. See, notice I have I here, but we're also using I in this for loop. So we do need to change up our variable names. So okay, so this should now work properly. But let me just comment this null terminator out. Okay, so here we have sort of the suffix of the word that we wanted to print. So, for example, for some reason, GO isn't being printed. So what's wrong with that? Oh yeah, so the problem is that as we recurse through the function, prefix is going to be empty, right? But we want to actually keep track of the original prefix. So in order to do that, we might actually need to use another recursive helper function. So here's our original function. What we'll do is call the function find prefix, and we'll pass it the trie, the prefix, and we'll just pass in the prefix twice. Okay, and in this function, we'll take in the trie, the prefix, and the original prefix, right? And we'll just pass this down in our when we recurse. Okay. Prefix. Okay, so and when we stir copy, we'll copy in the original prefix into the key instead of this prefix, which would be empty. Okay, so compile. Oh yeah, so I changed the function name, so I'm going to need to update my prototypes. So static void find prefix and char star original prefix. Okay, so now when we run our program, it will give us some words. So first gold, then we have good, then we have goody, then we have goopy for some reason. So the reason why this happens is because we didn't set a null terminator, right? Whenever we found the end of a key. So to fix that, we can go back here and uncomment this. Right, so every time we want to print a word, we want to make sure to add a null terminator to the end of it. That way it doesn't print out any extra characters that were added before reaching our current word. All right, so compile and run it. And now we get the words that we wanted, right? Gold, good, goody, and goop. Okay, so there is autocomplete. And we can actually try some other words, try some other prefixes. So let's try GOO now. So if we search for GOO, then we should no longer get gold, right? We should get goop, good, and goody. So if I compile and run, right, we get good, goody, and goop. Okay. And these words are being printed in alphabetical order because we're looping through the array in alphabetical order, and the first index corresponds to A, second character corresponds to B, so we end up, getting things in alphabetical order. Okay, but that is one application of tries. Right, if you wanted to search for, if you wanted to implement autocomplete and you had a hash table instead, right, then it's not going to be so easy to find all the words because, how do you know what keys are in the hash table, right? You're going to have to try every possible, word, every possible sequence of letters that starts with GOO, which might take a long time, right? There are a lot of possible words. So when we use a try, we're only descending down to, we're only going down to the nodes that we know exist, right? So we're saving a lot of time here. Okay, now here is another application of tries, was predictive text. Right now, I actually have a program for this. So here's like an example. So if you press the button 4663, that corresponds to the word good, but it could be some other words as well, I think. So goof, I think, is also another possible word. Home as well. So I do have a program for this. So what we have here is actually a keypad where each index corresponds to a series of letters, right? But since we are kind of low on time, I do have the solution. So let me just show you the solution. Okay, so what we have here is our function predict takes in a trie, a keypad, which is just an array of, which is just this array over here, right, which tells you which letters are displayed on each button, right? So, for example, 2 contains the letters A, B, C, and so on. Right, then we also have a set of keys, which will be stored into the trie, and the function takes in a series of key presses, right? So a string of key presses, for example, 4663, and in order to, find out all the keys that could correspond to the key presses, it first of all creates an array which is going to be used to store the key, to store the letters of the key as we go through the trie. And it's going to call our helper function, which takes in the keypad, the key presses, and the key, right? And the current index that we're up to in the key. Okay, so, this is complicated, but okay, so what does this do? So if the trie is empty, then we return, so classic base case over here. If we reach the end of our key presses, so we've gone through all the key presses, then that means we're at a node, right, corresponding to the first letter being GHI, the second letter being MNO, the third letter being MNO, and the fourth letter being DF, for example, right, if it was 4663. Right, so now what we need to check is if the current, if the key is actually in the trie, right, if the current node is a finishing node. If it is a finishing node, then that means the word is in the trie, so we should print it, otherwise we don't. Right, then we grab the first key press, right? So, for example, 4. Then, since 4 is actually a character, we're going to subtract the character 0 just to adjust for that, right? Then, so now keypad at index is going to be one of these strings, right? So what we'll do is to iterate through this string of characters and then try recursing into the subtrie corresponding to each of these characters, right? So we'll go through A, B, C, then we'll store A into the key and then recurse into the subtrie corresponding to A, right? Except we're going to, except here we're going to pass in the rest of the key presses, so everything except for the first key press, then we pass in the key, then we pass in I+1. Right, so similar to what we did with order complete. All right, but that is that, so you can have a look at this yourself a bit later. But that is all the applications, and that's all I wanted to talk about today. So that is the end of all the contents for this course. On Monday, we'll talk about a review, we'll talk about the exam. I'll release some information about the exam by the end of this week, so you can have a look, and you can, if you have any questions, then you can ask them during Tuesday's lecture. Right, but otherwise, if you have any feedback, then please feel free to fill out this form. A few people gave us feedback earlier this week, which was nice. If you have any more feedback, please fill in the form. And also, there is my experience. I'll talk about that on Tuesday as well. All right, so thank you all for coming. I'll see you guys on Tuesday. And there probably won't be a lecture on Thursday. Tuesday is probably going to be our last lecture. Okay. So see you guys then.